recording?
Yeah, it's recording.
Is it like framed up?
You're
Can you,
good.
like, move back or you're good?
You're good to go.
All right. Guys, last class we talked all about the mean value theorem. Last class we talked about the mean value theorem. The mean value theorem is really, really important. It's really important. Yanni, it's really important. As I may have mentioned last class, the mean value theorem is the crucial link between knowledge about a function's derivative and knowledge about the functions. Anytime you find yourself using the derivative to conclude something about the function, the mean value theorem is like at work somewhere in that. Let me give you a very simple example. Suppose I tell you the following pieces of information. That f of 2 is 3. And the other thing I tell you is that the derivative of this function is less than or equal to 5, always. And now I have a question. How big can f of 4 be? Alright, so don't shout it out. Everyone take 30 seconds and just like kind of think, or maybe even only 5 seconds if needed. Draw a little picture. How big can f of 4 be? Good.
It's 35.
Are you doing a pan if you are
Yeah,
you just getting
it's just
close
John
to the
Park. It's
bar?
just John Park.
Alright, Candia, what do you got?
13.
Yeah, 13. Candia, explain.
Because the most the slope can be is 5. So then just draw a little pointing and then on 5 and then out 5.
Yeah, okay, so she said, sure, f of 2 is 3. The derivative is less than or equal to 5, which means the most the function can be increasing at is 5, right? If it was constantly increasing at rate 5, it would be the biggest it could possibly be. So let's just suppose it is constantly increasing at rate 5. If it's constantly increasing at rate 5, then by the time you get to 4, it's like 10 bigger than it was. It's at 13, and so yeah, common sense just says the answer is 13. Okay, that is perfect logic, and that is the correct answer. And notice, what we have just done is we took information about the derivative, the fact that the derivative was less than or equal to 5, to conclude information about the function. So that must mean, if you believe me, that the mean value theorem is at work somewhere here. So can I give a more rigorous proof of this fact via the mean value theorem? Anyone know how to do this? What does the mean value theorem tell me? Anyone?
There must be at least one point where the function has a derivative, of the average.
Yeah. So okay, let's just write it out and see what happens. So apply the mean value theorem to f on the interval 2, 4. What does the mean value theorem say? Well, first of all, the mean value theorem is applicable. This function, I said that the derivative of this function is less than or equal to 5. That kind of implies that it exists. The function is continuous, it's differentiable also, or if it's differentiable, it's continuous also. So mean value theorem is applicable. What does it say? And Guan says that there exists a point C on the interval 2, 4 such that f prime of c is f of 4 minus f of 2 over 4 minus 2. Do you agree? Okay, but now what is this really? What is f of 4 minus f of 2 over 4 minus 2? Well, that's like just f of 4 minus 3 over 2, right? So the mean value theorem says there's some point c where the derivative is equal to that. But then what do I know about f prime of c for sure?
It has to be less than or equal to 5.
It has to be less than or equal to 5. So if f prime of c has to be less than or equal to 5, then that means this has to be less than or equal to 5, right? So suddenly I have that f of 4 minus 3 over 2 has to be less than or equal to 5. Oh, I don't know, I think this is kind of cool. Just like algebra 1 this out. We have just rigorously proved via the mean value theorem that indeed this function at 4 has to be less than or equal to 13. Okay, that is just a little something to get you excited about the many things that the mean value theorem can do for you. Okay, here comes another theorem which seems obvious, but its proof is quite tricky and involves crucially the mean value theorem. So here's the theorem. It doesn't really have a name. Here's what it says. If the derivative of some function is 0 on some interval a, b. So if everywhere on this interval the derivative is 0, what can I say about this function?
It's a constant.
Oh, John Park says he thinks that it is a constant function. Who agrees?
Right?
What's your justification, John Park?
Because of that rule from the thing from the textbook.
Rule from thing from the textbook. Could you be more specific?
Because like it doesn't increase or decrease in the slope for the tangent line thing.
Okay, someone. Okay. Hold on, John Park. Certainly, it is true that if you give me a constant function, then its derivative is 0. No one's disputing that because that's just like we can do that. There's like a derivative rule for that. But this is saying something a little bit more subtle, right? This is the converse of this. This is saying that if a function has a 0 derivative, then it must be a constant function. That is the theorem, by the way, and it is true. Then f is a constant function. Anyone else have anything deep to say about this? Why does this have to be true? Yeah.
Because if the derivative is 0, there's no rate of change. There's no rate of change. After that, there's no rate of change, so it's constant.
Yeah, that's pretty close to being basically the proof. Yeah, Timothy says, yeah, if the derivative is 0, it kind of means the function's just not changing, okay? So if a function is not changing, then wherever it starts, it's just not getting any bigger. Okay, how does the mean value theorem come to play? Well, the mean value theorem is sort of saying that on every interval, there's some special point which kind of represents the function on that interval. That's how I think about the mean value theorem. Over here, for example, I just applied the mean value theorem, right? What the mean value theorem really says is there's some special point c which might